Okay, so lesson 2.4, connecting differentiability and continuity. Differentiability. What is differentiability? For a function to be differentiable on an interval. So for this to happen, the derivative exists at each point on an interval if. So the derivative would exist everywhere on that interval if the graph is smooth and continuous at each point on the interval. So if you have some interval from A to B, say from A to B, and the graph is smooth, smooth like this, it would be differentiable everywhere. But yeah, for that situation, this is it's differentiable everywhere. But if it does go something like this though, from A to B, even though it's smooth, and it does something like this, and then it does this, it will not be differentiable where it just goes straight up and down. So if the function goes straight up and down like something like right here, then it wouldn't be differentiable here, even though it is smooth and continuous. So you gotta be careful with some definitions here. Okay, so we continue on. The derivative fails to exist at some point on the interval if there is a discontinuity of any type on the interval. There is a hole in the function. So say we have a function and the function does this. Okay, say it's a straight line, but then it has a hole. So if it has a hole, then it is not differentiable from, like, say, A to B. From A to B, because at this point where it is not continuous, it is not differentiable. But would be differentiable everywhere except here. But because it's not differentiable at here, then it's not differentiable on the whole interval. That's all it's saying. So if it has a jump discontinuity, it wouldn't be differentiable at one point of it. So if you got something going like this, a function going like this, and something going like this, no, let's see, no, that's not it. If the function is going like this, say a function is here and it goes this way, and then it has a jump discontinuity, and it does this, then this is called jump discontinuity, and it wouldn't be differentiable there. Vertical asymptote. Well, that's going to what I just said in the previous example. If anything like, say, a function that's going like this, it wouldn't be differentiable here because it would have a vertical tangent. So that is not differentiable at that point. All right. Also, it would not be differentiable for a function that has a corner. A good example would be the absolute value function, and it wouldn't be differentiable at that corner right there for the absolute value. It has a vertical tangent. That's the one I keep talking about. Vertical tangents right there. That is not differentiable here or here. Okay, so problem number 1. Identify any x values of the function that are not continuous or not differentiable. So where is it not continuous for this graph? Not continuous. So we can already see that it is not continuous here. It is at x equal -3, and it is also not continuous here. So at x equal -3 and at x equal 4, it is not continuous. X equal -3 is a removable discontinuity. We can fix it by defining it. So it's fixable. But this jump discontinuity is not fixable. So that x equal 4 is a non-removable discontinuity. It's a jump discontinuity. Continuous, but it is not differentiable. It would be continuous here. You see that here it's continuous, not differentiable because it has a corner, and it has a corner here as well. So at x equal negative 2 and at x equal 2, it has a corner and it has another corner there. It would be not differentiable because of that. Problem number 2, which of the following functions are not differentiable on at least one point on the reals? Y equals x squared, that's the quadratic function. That is smooth and continuous everywhere. That is differentiable everywhere. So it is continuous and smooth everywhere. It is differentiable everywhere. Y equals 1 over x squared. It will have a vertical asymptote at x equal to 0. So it has a vertical asymptote. So it wouldn't be differentiable everywhere. So here you got to be careful. It's just not differentiable, but it is differentiable where it exists, but it is not differentiable everywhere. This one has a hole at x equal to negative 1. So here is x equal to negative 1. It would have a hole there, so it is not differentiable everywhere. This one is the one that goes something at x equal to negative 3. It goes this way here, and then it goes this way here. It's negative 1, positive 1. So jump discontinuity, not differentiable at x equal to negative 3. So it has a jump discontinuity at x equals negative 3. And it's not differentiable on R. Last problem for this section, is this piecewise function differentiable at x equal negative 1? So when it's talking about differentiability, it has to be differentiable at x equal negative 1, coming from the left and from the right. So basically, we can go ahead and just find the limit coming from the left has to equal to the limit coming from the right. So we have to say that the limit as x approaches negative 1 from the left of this function f of x has to equal to the limit as x approaches negative 1 coming from the right of the function f of x. And if that is true, then this would be differentiable. So let's do that. Find the limit as x approaches negative 1 from the left. So coming from the left, we just got to plug it in here. Okay, so we're going to just go lim as x approaches negative 1 coming from the left. Plug it in, negative 1. 5x is negative 1 squared plus 3x is negative 1 plus 2 has to equal to lim x approaches negative 1 from the right. And you're going to plug in negative x is negative 1 minus 3. It has to be true. So that's going to be 5 minus 3 plus 2 has to equal 2. 7 minus 3. 5 minus 3 is 2. 2 plus 2 is 4. And 4 is equal to 7 minus 3 is 4. So that is true. So that would be differentiable at x equal negative 1. So we use that whole limit definition of it, but the way I did it, this works as well, but it's much more work. There actually is a third way of doing it. A third way of doing it would be this way. Just assume that it is differentiable. So the fastest way to do it is assume that it is differentiable at x equals negative 1. So you could just take the derivative from the left and evaluate, and take the derivative from the right and evaluate it. And if it's true that they are the same coming from the left from the right, then it would just be that it is differentiable. Take the derivative from the top. So from the left, it would be what? 10x squared. 10x squared plus 3 has to equal 2. And then we're going to evaluate it at x equal negative 1. So take the derivative of the bottom function is negative 7. Okay, so we already got that the rate of change at -1 is -7. It is linear. For this one, let's plug it in. Now for this left side, plug in x is -1, so it'll be 10. X is -1 squared plus 3 has to equal to -7. So that would be 10 plus, let's see here, what happened here? X is -1, the derivative, oh, x is -1. So here, this on the right side is 1. X is -1. We've got to plug in, the derivative is -7. Hold on. If we do plug in, let's take the derivative, it is -7. So that one's -7. To derivative, that's just -7, yeah. So this one here, it'll be 10x. No, it's just 10x, man. So this on the left side is 10x plus 3. And now when we plug it in, so on the right side is -7, and now plug in x is -1, that would be -10 plus 3, then that's going to be -7 equal -7, which is true. This is a much faster way. I kind of messed it up here, but this is a much faster way of doing it. Good. All right. So that's it.